Hi guys, Assalamu alaikum. This is Arif. In this video, we are going to see how we can write messages to console using system Verilog and VHDL programs. By messages, I mean we have signals in VHDL and we have tags and wires in the case of system Verilog, and we are going to see how we can write all these onto the console window. And by console window, I mean this window, which here is the transcript window in the case of Questa simulator by Intel. So in order to do that, I have selected the design code and test bench of our program counter, and during this video I am going to show you how and why I have selected a program counter to show this. So this is a design file of a system Verilog project first, and in this we have defined a module named PC, and it has these inputs and outputs where you can see here. So after that we have this always block, and in this is actually implementing a register or a 8-bit D flip-flop, and here we are assigning the value of next PC to our PC. And after that, this is actually a sequential logic in this code, and we are using the non-blocking assignment here. And after this we have some combinational logic because our program counter is going to implement the logic of branch as well. So that's why in this always block we are using this inputs like power, stop, enable, branch, enable, and PC. And after that we have some logic to implement our program counter, and here we are saying if power is equal to 1, then do all this functionality, or if power is equal to 0, then else set this next PC to all 0-bit values. And once power is going to be 1, for that case we are going to check stop enable signal as well. If this is going to be 1, then we are going to stop here. Our next PC is going to be PC. We are no longer increasing our PC. And else if stop enable is going to be 0, we are going to say increase the PC, but according to this branch enable signal. If branch enable is going to be 1, take the next PC to branch, otherwise take the next PC to PC plus 1 to increment it. So this is our program counter main design code, and after this I am going to show you its test bench as well. So its test bench has these wires and reds, and then we are calling the main module here PC. And after this initial block, first one is going to implement our clock signal. We are going to run this clock signal here, and then after that this second initial block we are going to use to give our inputs like power is an input, stop enable is an input, branch enable is an input, and branch PC is an input. So we are going to try here different combinations after 10 nanoseconds delay, and after this we are going to finish our code here, the end module. So this is our complete program. Now let's compile both files and try to simulate it first so that you can see how it is behaving. So let's run this simulation. And we are going to see here this one, the way our PC is going to increment according to next PC and then the branch PC. This is the logic. I am not going to explain it to you. You can find some other video, but we are going to concentrate on this window. We are not seeing any messages here. This run command just we see, right? So we are going to implement now this code, the test bench code like this, that we can see all these cycles. This is clock cycles, the way they are running, and these timings in this transcript window and these corresponding values as well, right, onto the console window. So let's go to this code, and now we have to include some code lines to use some functions. So these are those code lines which I am going to include. I have included an other initial block. Here I have defined actually two extra variables here already, which are stop signal and then a cycle signal, and those are both of reg type. Okay, so there are two ways to check our signals step by step. First of all is that we can either do the timing the way you guys saw in the wave window, like 10 nanoseconds after 20 nanoseconds after 40 nanoseconds, this is changing, that is changing. The second one is you can see the clock cycles. Okay, at this clock cycle or at this cycle it is doing this, at that cycle it is doing that. So one approach is that in order to check stepwise our signals at the different stages of our program, we can define a cycles variable like this and increment it. And the second one is we are going to use the time, like after 10 nanoseconds this is going to behave like this, after 40 nanoseconds it is going to reach at this stage, right? So for the first case cycles, and I can tell you one of those is enough. Either you can define a cycles variable like this and do, or you can use the time, which I am going to show you now. So this block we have finished, and stop also we are initializing it to 0, and I am going to show you later how we can actually stop this program as well using a function, and we are going to do both in system Verilog and VHDL these things as well. So stop signal is going to stop our program at a specific time according to a requirement. And this is one of the reasons I have selected this program counter design for this implementation. So after this always block comes, and we are going to say always at negative clock edge. So why we are using negative clock edge? We can use here positive clock edge as well, because we are starting our clock from 0. If this clock is going to start from 1 here, we can use negative, we can use their positive edge as well, but right now we are going to use from the negative edge to cover all the things. And after that we are going to say if stop. So if our stop signal, which is going to stop our program, is true, then we are going to say okay, stop this program. We are using here this display function like this, and we are going to print out our PC by %d as well also. And this %d first is going to give us our number of cycles here. Second %d is going to give us the PC inside this display function. So this display function is actually one of those functions which we can use to display values or our signals onto this console window, wires or tags, whatever are there in the case of Verilog. And this first display function, This is where we are checking the time as well. This percent %t is for this dollar time function, and this percent %m we are going to use because we want to see the name of our this test bench module as well. This module name is test bench. We are going to see its name onto the console window as well. So that's where this percent %m is coming. So now two things. We can check the signals according to the cycles, number of cycles, stepwise, or we can use this timing. So both we are using, but one of those is enough. We can skip these lines like this, and we can check our signals according to these number of cycles, or we can skip these lines as well, and we can check according to the time. But here we are going to use both. So once stop is going to be 1, we are going to print out these values. Next, we are going to use this logic inside our program. That's why we are using this program counter, because it has some if else statements. We are going to say, okay, if power is going to be 1 or 0, what we are going to do here? We are going to go here. We are going to say, okay, if there is no power, we are going to say, okay, print out the PC, next PC, module name, timing here as well. We are going to print out all these things. Cycles we are printing out due to this percent %d. Power we are printing out due to this percent %b. It is on or off, and same way this PC percent %d. These percent %d's are used for the integers. Percent %b is for like 1 or 0 bits binary. So same display functions we are going to use, and after that we are going to say in the else statement we are going to say if power is going to be 1, now check stop enable just like this. We are doing here if power is equal to 1, then check stop signal as well, stop enable. And we are going to say if stop enable is going to be 1, what we are going to do, we are going to check all these values. We are going to print stop here as well, and we are going to stop this program. We have to stop this program, and here we are going to check, okay, next PC's value was this, present PC was this, number of cycle was this, and then we are going to say since stop enable is going to be 1, we are going to make the stop equal to 1 because we have initialized it to 0. So here we are going to stop the program, and after that we are going to check the branch enable signal the way we are doing here, branch enable within this stop enable. And we are going to say, okay, if stop is going to be 0, then check branch enable signal. If branch is taken, then branch enable is going to be 1. Go to branch PC, this value. Branch PC, we are also here printing by percent %d, next PC, PC power, and the cycle number. And timing here as well, percent %d time, right? And now if not branch taken, that means we are going to increase our PC by just 1. We are going to say again, print the time, name of the module, using the display function, check the number of cycles, power, PC, next PC, and percent %d, last one is going to be doing this PC plus 1, increment PC, that's why we are writing here. So this is our complete program, and are for the if conditions here. We are using the same logic. Now let's save this and compile this. Check these signals so that we can see the signals in wave window as well. And we are going to try to see using display function those onto the console window as well. So run this. So we can see our cycle, the stop signal is going to go one here, and the PC values are going to increment like this. But now check this window. We are going to see these messages. So after this note, we are going to see, okay, cycle is 0, power is 0, PC and PC, these values, right? And after that, we are going to see this along with the time. What we are going to see here, instance, that module name, test bench. Time is going to be 0, 10 nanosecond. All these signals, we are going to see increment PC by 1. Next PC is going to be like what? According to the time. This is our time. This is our number of cycles. We can use both or any of those. One is enough. So stop program we are going to see as well. But the program is not stopping here actually. We are going to see some values here as well that we need to figure out later. Right now our signals are working fine. But let me show you one thing actually. This time 120 nanosecond, you can see this first of all this space. Why this space is there so much long? Then you can see 120 nanosecond is not written the time unit. That we are going to do now. We are going to use another function to implement this. So we can come here and we are going to include this code line. This is actually $time format function. This -9 is for nanoseconds. This up to 2 decimal places we are going to see our time, and this nanoseconds we are going to print like this, and this 15 is this space which I was talking about. Here you can see time is written here and 110 is written here. So this 15 we can vary to make this space bigger or smaller. Okay, and now we can just save this program. Simulate this program. And run this program. So here we are going to now see here, you can see here 120 nanoseconds. We are seeing here module name as well, right? 90 nanoseconds. So this way, one is number of cycles, this 8, one is time to check at what level our program is. Now let's end this simulation. So instead of using our this $display function, we can now try some other function as well. So we can comment out these two lines and we are going to use some other function. So now our program is ready with the $strobe function. Instead of display function, we are going to use this function now to print out all those values onto the console window. Okay, same %t $time function we are using here. And no need to run now the wave window simulation, just run it from here to see the console window. So these values we are going to see using the $strobe function. So this is the way at each step you can see the results of your simulation using these two functions. And now on the similar pattern, I am going to show you another function is available, which is called this $right function. So it is going to behave the same way. Just one thing to remember is that in the case of $display or $strobe, we are going to go to the next line automatically. Like this function is going to implement this thing, and it is going to then go to next line to implement this next $strobe. But in the case of $right function, the line is not going to change. So you can always add this slash n. Look here, we are not adding any slash n. But in the case of this $right, we are adding a slash n here too. So that this function after executing, it goes to next line and we can see our messages accordingly. But I am not going to include these code lines. You can check it at your end. But this is the way we can use $right function as well inside these if else statements, the way our logic is changing. So now I am going to show you that we have seen the function of this cycles, the function of this $time as well. And actually I am going to show you one more function, this real time. Instead of $time, we can also use to see our time at the console window at each step of execution. Real time like this or $time. Okay. And now we are going to see what is the function of this stop, how we can use this to stop our simulation, because our simulation was not stopping although we saw this logic is actually working. Stop was changing, and we are implementing stop. Like here stop is not 1 because we have initialized it to 0, but here it is becoming 1, right? So once it is going to become 1 at the next cycle, we are going to see this condition if is going to become true, and we are going to see stop program onto the console window, and it is going to stop as well accordingly. So in order to do that, we can use this function $finish so that it actually stops the program. $finish. So let's save this, compile this, simulate, and let's run the simulation. Actually, let's see wave as well. Waveforms we need to see as well that those are stopping, because previously we saw logic was working fine, but we were getting more values of PCs as well. So let's run this. Now you can see here, are you sure you want to finish? Okay, so if we are going to press here yes, it is going to exit this whole Questa software. We are not going to do that right now. We are going to say no, and then we are going to see a break here at that line. This is the line 82 you see, and break at this line. We are seeing this message to the console window. Let's go to our waveforms and see, and you can see after we are putting here stop enable, next clock cycle, no longer values of PC has stopped. So this is the way we can choose this finish function, $finish, to stop our program. And now I am going to show you one more function which we can use this $stop as well to end our simulation the same way. Okay, so this is the way we can break our program during the simulation where we want it to stop according to our logic. So this is the way actually guys we can see the time onto the console window, the time units, the module name using these display, strobe and write functions and the corresponding signals as well. So now let's flip over to our VHDL program and we are going to do the same thing using the VHDL project as well. So I am going to open now the VHDL project and let's go to its design file first, and we are using here the program counter on the same manner we have written this code. And in this architecture again we are saying here this is our 8-bit register or a D flip-flop. Inside the program counter we are assigning here next PC to PC, and in this next process block we are going to check all the inputs and we are going to take the decisions due to this if else statements. And we are going to say here like if power is 1, check stop enable. If power is going to be 0, next PC is going to be 0 0. Okay, and if stop enable, next PC is going to be PC. Else if stop enable is 0, we are going to check the branch enable. If it is there, we are going to put the branch PC inside next PC. Otherwise, if branch enable is 0, next PC is going to be PC plus 1. And finally this else. So this is just on the same pattern, our program counter. And this logic we are going to use in the test bench as well. So in the test bench, we are going to say here like this is the test bench entity, test bench, then architecture. We are using this component PC, and after that we are going to call the unit PC and use this port map to map its inputs and outputs using these signals. And after that in this process block we are going to give the logic of our clock like this. It starts from 0, and after that in this process next process block we are going to give the inputs to our signals, input signals like power, stop enable, branch enable, different combinations we are going to try. And then we are going to say end this process, and finally end architecture here we are going to say. So let's run this program like this first of all, because we want to see first of all how it is behaving. And we are going to go to this wave window, select these signals, and let's run this program. And after run we are no longer seeing any messages inside the console window, this transcript window, and we are seeing here these PCs, way their values are changing according to inputs and outputs, but no messages onto the console window. Now let's close this simulation and try to see the same timings like this. This is our, where is the clock? This is our clock. These are the cycles, right? And these are the timings. So according to the cycles or the timings, we can see, okay, at this cycle, what is the situation? At that cycle or timing, what is the situation? And now let's modify our test bench code and add some additional functionality. So now let's check this code. We are going to define some extra signals as well, like the cycle signal to see our program according to its different stages, cycles, and then the stop signal as well to stop it. So you can see here we are initializing these cycles to 000 here as well. And so in this process block, what we are doing, we are again starting from the falling edge because we are starting our clock from the zero. If we are going to start the clock values from one, we can use here rising edge or clock tick event clock is equal to one, like that. And after this, we are going to start the cycles, increase those by one. And here we are saying if stop is going to be one, then print this message, and see how we are printing this message. This report keyword we are using here, and these are the things with which we are changing these values to integers this way. To integer unsigned we are using here, and I am going to show you that what libraries we are going to need. Yes, this library we are going to need to use this to integer, this library for this plus sign. So we can see here we are saying here cycles, number of cycles it is going to give us onto the console window. And after that we are using here and to concatenate this string we are concatenating with this, and then again and to concatenate this PC string, and then and concatenate PC's value we are going to get from here in terms of integer, then stop program after this and then else we are going to say if stop is going to be 0 our program is running. Then we are going to say okay, if power is 0 then show this show this report, number of cycles, power, PC, what is the situation. Okay, and after that this else statement we are going to say okay, if stop enable is going to be 1, make the stop signal equal to 1 here and report these values. Okay, next PC power on the same pattern the way we were doing in the Verilog code, and else if stop enable is 0 our program is running, branch check, if it is 1 take the branch, you have to take the branch, and then we have to see these values onto the console window. Next PC branch to this value, same integer we are using here, same logic. These if else statements we are using this here, we are just using here. See, if stop enable, if branch enable, and then else We are going to increase PC by 1 and we want to see that onto the console window as well. Increment PC, we can name it. But look here, we are not doing any function to see the module name, which is again test bench, actually the entity name, this entity test bench, right? We are no longer using those time functions to display our time and everything, right? But let's now compile this program and see how it is going to behave using this report. So let's go simulate. Drag these values here, run this simulation, and we are going to see the same thing. We have the stop, here it is becoming 1, but the next PC values we are getting because it is not actually stopping this program. But look here, this time in nanoseconds, automatically we are getting instance test bench, right? This number of cycles we are getting here, time units we are getting as well. Everything automatically is there in the case of report. Okay, these are the power PC values, time, its scale, instance, test bench, everything is there. Same output we are getting here in the case of VHDL as well. So just one function can do all the things which our display and the other functions were trying to do in the case of system Verilog. And now we are going to see how we can actually stop this program at this point using the stop signal. Our logic is working fine, but now let's try to stop it in a real manner so that we can believe that actually this is happening as well. So for that, there we used $finish. Here we are going to use this assert, false, report, test OK, severity, failure. So this line we are going to include now. Here we are making stop equal to 1. So in this if block, we have to use, because here it is becoming 1, because if stop enable is going to be 1 then. So now let's save this. Compile selected. Let's go here, test bench, simulate. Go to this wave window. And now we see break in process line. So here we see this break 96. You see line 96, line 96. Here you can see. Here it is stopping where it is supposed to stop. And now let's go to this wave window and we are going to see PC is going to stop. So here it is putting the stop signal high, and in the next clock cycle we are no longer seeing any update to any PC value. Here they were changing next PC, everything. But now, so let's end this simulation. Now I think you guys have seen how we can write the messages onto our console window in the case of system Verilog and VHDL as well. And as well as you guys have learned how you can use some signals or functions or keywords to stop your simulation, your program at a specific step or time. This report is giving us time function. It is displaying onto the console window as well. It is giving you timings as well. Everything it is giving. Just one function is enough in the case of VATL. So thank you guys. I hope you guys have enjoyed this video. Have fun.